Good. So before to prove this, this is very important theorem, and it is important in all courses. Before to prove it, we prove some properties which are of convergent sequences. So you know from the course of usual analysis, if sequence xn converge to x, it's implied xn is bounded. No, if x is finite. So any convergent sequence is bounded. This you somewhere. It is very simple. You can prove this easily. The same we can prove for normed spaces. So now we are in a normed space. Then how to prove the xn bound? We write xn norm. It is equal. We put here xn minus x plus. Okay, for the moment we go to quick. Plus x. And now we use triangle inequality. The sum of two vectors. This the third side. This is this vector plus this vector is less or equal than the sum of the lengths. So starting with some number, this is less than epsilon. And this is just number. So this is less or equal by some constant. The only thing which you use here is triangle inequality. This slide, but okay. So any convergent sequence in normal space, in particular in Hilbert space, is bounded. Now another result, also very simple. We formulate this lemma, because it is also simple but important. Lemma function f x y, scalar product of x and y is continuous function on Cartesian product of Hilbert space on itself. Is continuous Hilbert space by itself to real line. So scalar product is continuous function of two variables. Scalar product has real values, so this is function from Cartesian product of two Hilbert spaces into real line. Now the proof is also a simple proof. Suppose that, for example, AN converge to A, BN converge to B, BN converge to B, and I destroy this theorem beside of Parceval equality, which is our aim. Beside of Parceval equality. Then we want to prove that F AN BN converge to FAB. We want to prove that if we have two convergent sequences and we put them in scalar product of these convergent sequences will converge to their limit, scalar product of their limit. Okay, so how to do this? We write AN BN minus A scalar product B, and what I shall do? I shall do the following: AN minus A BN. Then I should add this A Bn minus AB. And then I would also subtract also Bn minus B. I destroy one Parceval equality. I shall write this again. So we want everywhere to get this an minus a and bn minus b. So an minus a, then bn minus b, and here would be who with plus an minus a scalar product b. And then it's also good to write this in which way. So this is linear. This is linear with respect to this argument. So I can write the last term as a is the same, and here bn minus b. Oh, so this guy, if you open the bracket, it is this guy. I use triangle inequality for usual absolute value. It is less or equal the first, and in parallel I shall use, I shall use would be an minus a, bn minus b plus. This is just triangle inequality for absolute value plus a, bn minus b. Yeah. And now for all these scalar products, I apply Cauchy-Bunyakovsky-Schwarz inequality. Cauchy-Bunyakovsky-Schwarz inequality. So it would be less or equal. Here it is norm an minus a, norm bn. You will see that all these guys go to, this go to 0, this go to 0, plus here an minus a b. And here plus norm A, norm Bn minus B. So all three terms go to 0 because A minus B, A minus A, and Bn minus B go to 0. So scalar product is really continuous, and the only thing that we used, it was Cauchy-Bunyakovsky inequality. Yeah. So this was the key point of this proof. Because of Cauchy-Bunyakovsky-Schwarz inequality, scalar product is continuous function of two variables. We shall save this. We shall hope to be, or maybe it's better this way. So I don't know how it would be. Yeah, so we prove this lemma that scalar product is continuous. Now we go back to our theorem on Bessel inequality. We go to our theorem on Bessel inequality or Parceval equality, on Parceval equality. And what we know, proof. We know that En is basis. So we know that X is the sum, and from 1 to infinity, Xn, En convergent in H. Now let us write the square of the norm. It's just scalar product X by X. And then put instead of X this series. So it would be scalar product n from 1 to infinity Xn En. And for another series, for me, it's more convenient to use another summation index. It's my right to use summation index, what is convenient for me. Here I use M. Now, who is the sum of series? It's the limit, it is sum, this limit, and go to infinity, sum n from 1 to n, partial sum, xn, en, and here is also limit, and go to infinity, partial sum m from 1 to n, xm, em. But just now in lemma we proved that scalar product is continuous function. And we can change scalar product and limit. We can change two operations, limit and scalar product. And we do this. We change limit and scalar product. Limit n to infinity. And here it's sum x or u until n, xn, en, and from 1 to n, xn, em. But now scalar product is linear with respect to both arguments. So we can change the order scalar product and sum. And moreover, coefficients, Fourier coefficients can go out from scalar product. These are numbers, these are scalars. We know that scalar product has, for example, this property. And we know that also why is that? And the same with respect to the second variable. So scalar product is linear with respect to both variables. Scalar product is linear with respect to both variables. So now we change this sum, this scalar product, and numbers go out. Now maybe we go into details, but it's first time, so it is okay. Maybe okay. And here is what we want. This is this En, Em, which is equal Kronecker delta symbol delta Nm. So double sum disappear, and we get this limit and go to infinity, sum n from 1 to n large, xn square. And this is just the sum of this series. By definition, this limit of partial sums is just the sum of this series. So we proved Parceval equality. It's equal sum from n from 1 to infinity, xn square. So the square of the norm of the vector in Hilbert space is equal to the sum of squares of coordinates with respect to the orthonormal basis. But it was not so complicated problem. We just wrote into details. In principle, we can change scalar product and series already here. In this line, we can take this series out, and we will get again this scalar product En by Em, and they will cancel each other. We wrote the sums, we use the scalar product is continuous. It is very detailed proof, but in fact, the statement is very simple. So the square of the norm is equal to the sum of squares of Fourier coefficients. Now it is more interesting statement. For example, we have some orthonormal system. How to understand that it is a basis? That really any vector can be expanded in the series with respect to this system of vectors. Of course, you can just try to do this straightforwardly, but typically it's not easy. So now we formulate such theorem, such criterion of that En is basis in terms of Fourier coefficients. So how, by using Fourier coefficients, to understand that some system of vectors is really orthonormal base. Of course, first of all, it should be orthonormal, but why any vector can be expanded in this series with respect to this system? So now and it's important question. It's important question because to check that some system is orthonormal, it's very simple. We just multiply the scalar product, calculate. For example, in L2, it would be just integral of product of two functions. But to understand that this series would converge to any function is not so simple. Theorem. Let En be an orthonormal system M in a Hilbert space H. So this means that En Em is equal delta Nm. But we don't know that it is a basis. Suppose for any x in our space, Parceval equality holds true. The Parceval equality holds. So what we do? We take a vector, we calculate its Fourier coefficients, we write the sum of squares of these Fourier coefficients, and if this sum of Fourier coefficients squares is equal to the square to the norm, so suppose that we have Parceval equality. Suppose that for any vector, the sum of its Fourier squares of its Fourier coefficients equal to the square of the norm. Then this is a basis. Then En is a basis. So any x can be represented as the sum xn En. Well, this is convergence series. Convergence then in H. Where series converge in H. If we take into account the previous theorem, finally we shall get that system En is orthonormal basis if and only if Parceval equality holds. The Parceval equality is criterion that our system is basis. So what we would like to prove? What we want to prove? We want to prove that the norm x minus these partial sums n from 1 to n, xn En square go to 0 and go to infinity. We want to prove this. Then it is by definition means that this series converges to x. This series converges to x. So let us calculate this. Let us calculate this thing. Yeah? So what is the square of the norm? Minus n 1 to n xn En x minus sum n from 1 to n xn En. And now we should open the bracket. open the bracket. So it would be, maybe we go up, so let's open the brackets. Yeah. Just a bit down, and here I clean. Would be x by x, so x multiplied by x, minus x, I multiply it by the sum n from 1 to infinity, or not to n large, xn en. And whom we have? We have also minus sum n from 1 to n xn en multiplied by e. And finally, we have plus. We have plus sum. We have plus sum n. I should multiply this by this. When I open brackets, so this sum will go out, this sum will go out. I again will get en multiplied by, so everything disappear. So the last term would be sum from 1 to n xn squared. So the last term would be just the sum of squares. Because when the bracket is open, everything will start to disappear. Now we would like to work with these guys. Now I put this out. I put this out, but then I multiply x by en. But what was our formula for Fourier coefficients? We precisely had that this is x en. So Fourier coefficients. So if I multiply this, finally it would be x scalar product en, but it is xn. So now it is equal. I would like to preserve this Parceval equality. This we need. So and I destroy everything what is below. And I continue here. Maybe not so convenient that I should destroy everything, but I would like to be just in front of this. So continue. Now I can already put the x by x. This is square of the norm. This is sum and from 1 to infinity xn square. Here it is minus. I even do more because it is symmetric. It is these guys are the same. They are the same. This multiplied by x and x multiplied by this. It's the same because you know this scalar product is symmetric. So I immediately can write minus 2. Here is the sum n from 1 to n xn square. And the last term was already calculated. Plus the sum n from 1 to infinity xn square. Now when n go to infinity, so n go to infinity, this is sum n from 1 to infinity xn square minus 2 sum n from 1 to infinity xn square plus sum n from 1 to infinity xn square. This is 0. So the difference between norm x and partial sum of series with respect to orthonormal basis goes to 0. So really x can be represented as the sum of series. So if Parceval equality holds, then our system is a basis. Of course, we should first check that it is orthonormal. This is orthonormal. So this is the end of the abstract machinery. the end of abstract machinery. And now we go to one concrete orthonormal basis, which give us, I can say, usual Fourier series. So write the title of how to call it. We can call it so Fourier series with respect to trigonometric base. Fourier series with respect to trigonometric basis. Okay, so our Hilbert space H is L2, and at the beginning we can consider concrete interval, but then we generalize to arbitrary, from minus pi to pi. Now we consider trigonometric functions, and they are well defined on the segment of the length 2 pi. So these are functions which are square integrable on this segment. So scalar product here is fg is equal integral from minus pi to pi fx gx dx. So this is scalar product on our space. And now consider such sequence of functions. So 1, then cosinus x, sinus x, cosinus 2x, sinus 2x, and so on. Cosinus nx, sinus nx, and so on. So consider this system of functions. You can enumerate them. For example, this would be E1, E2, E3, and so on. So this is the system. Of course, all these functions are square integrable. They are continuous, and the integral, of course, finite. Of course, integral is finite. We can write such equalities: integral from minus pi to pi, cosinus nx, cosinus mx dx is equal 0, n is not equal 10. And all these integrals for different, they are also cosinus nx, sinus mx dx is 0 for any n. And the last one, sinus nx sinus mx dx is 0 n not equal n. So these are usual integrals which you studied in the course of analysis. And to calculate them, you should remember the formula of product of cosinuses and the product of sinuses. I don't remember. Now we check who remember. So we need such formulas. For example, cosinus alpha na cosinus beta is equal. Somebody remember, not?
You can use Euler's formula.
Yeah, this I can do, and this I plan to do, but maybe okay. So since we all so lazy that we don't remember this formula, we shall follow your suggestion and use Euler formula. We know that this is E alpha plus E minus E alpha divided by 2. And this is E beta plus minus E beta divided by 2. Divided by 2. Okay, so let us calculate this integrals. No, there's such notion overqualified. When you will get your PhD and come to some Fourier to search for job, they thought, oh, guy, you are too smart, too clever. We don't need such people. It's maybe surprising, that because all your education at university that you should be more and more, you should have good results for exam and so on. But when you're coming to find job, very often they're afraid, clever people. They thought, no, our firm does not. Especially in Smoland, they like simple people who do simple job. When I came here, I was surprised, but it's few my PhD students, they had difficulty to find job, but those who were just master students, they found it's much easier. And those who had just diploma, they were the first. Now, of course, the explanation is very simple. Less your educational level, less salary you will get, yes? So for PhD, you should give quite high salary. If you just got diploma, okay, you get little and you are happy. But it was really for me a kind of shock because I had very excellent lady who get very excellent PhD and nobody wanted her. And very simple guys who got diploma and so on, they found immediately job. Okay, so we are overqualified. We calculate this in this way, but why not? We are not looking for job, yeah? Is there still, when you go to Teleborg, there is some tunnel to Teleborg, and it was written on over the slogan, till Wirklichkeiten, to reality. So here in campus you have ideal world, but then you go to town, this is reality, till Wirklichkeiten. So now we are in ideal world, yeah.
I think the formula is 1/2 of cos A minus alpha minus beta plus 1/2 of cos alpha plus beta.
Look, alpha minus beta plus cosinus
Cos alpha plus beta.
alpha plus beta.
And
One
1/2 of that.
1/2. You will find job, yes, definitely. It's not that you will not find job also because you remember formula. Okay. No, everybody will find job because finally all my students, they have jobs and very good. One of them works in Stockholm in some financial corporation, and he claims that he has salary 150,000 kron per month. Can it be in Sweden? Or he's lying just to tell that she is higher than I? Salary.
With bachelor?
Yeah. They do some finances. Per month. He was not best. He was not best at all. Oh, he was French. It is interesting that in Sweden there is prejudice to French. In Russia, French were a kinds of gods. So French is well educated, he's elegant, he's very great cultural background and so on. In Sweden, a few times I thought, oh, French, you should be, it's not so, be careful. And I thought, why so different? But on the other hand, okay, I saw a few French movies from 60s. And there are many Swedish guys in these movies. Typically, they are very simple. So they imagine Swedish, they cannot eat with right forks and so on. When they come to women, they behave as and so on. So this is, I think it was some, I can say, cultural competition between Sweden and French. You have even king from France, yes? Yeah, one of Swedish kings was from France. So there was, and moreover, you got to know Carl Johan Swamp only from French. So before you did not know that you can eat it, or it's not the right story. Carl Johan Swamp. Some people told me that in Sweden only French king, who was the Napoleon Marshal, when he came to Sweden, he went to forest and told, "Oh, take these mushrooms." Swedish people told, "No, we cannot eat them." He told, "No, in France we eat them." Is it right story? Nobody knows because the king already dead. Yes, king's dead, and we will never know this. Okay, so there are many prejudices about, for example, all people believe that Russians drink vodka. Many Russians drink vodka, but not everybody, because it was academic Octiden just on Friday. And all people told me, you don't want wine, maybe you'll find in bar vodka. I never drink vodka, I like French wine. I like French wine, but not vodka. Okay, so it was story around this formula, and now we can calculate it, yeah? Because of this advice from minus pi to pi. Here will be, for example, this one, да? For example, this one. It would be cosinus n minus mx plus 1/2 we forget because we expect that it would be 0 minus pi to pi dx cosinus n plus m x dx. Now see, when we integrate, for example, this guy, shall we get 0? We get 0 with this formula. Okay. This exponent is better. This exponent is better. So it would be sinus n minus mx divided by n minus m, and from minus pi to pi. It is 0 just because sinus is 0. Yes, I was a bit surprised that it goes, and this minus from minus will be plus. So it is 0. And the second is also 0 because sinus is 0. So we calculated that this integral is really 0. If you don't remember this formula, you again use this two smart method you calculate. So these trigonometric functions are orthogonal. They are orthogonal. Trigonometric functions on the segment minus pi, they are orthogonal. Now we want to know what is the norm? So now we want to find the norm of this trigonometric function. Oh, what is square cosinus nx square norm? It is integral from minus pi to pi cosinus square nx dx. And here even I remember how from cosinus square go to just double. Yeah. So minus pi 1/2 1 plus cosinus 2nx dx. If you integrate cosinus, it's again sinus, and if you put pi, it's disappear. So the only who give us the number is 1. The only who give us the number is 1. So it would be 2 pi divided by 2, it would be pi. So the norm of cosinus square is pi. And the norm of sinus nx square is pi. 1, it's a bit different. The first in our basis was 1. The norm of 1 square, it would be just the length. It would be 2 pi. Now to get orthonormal basis, we should normalize. We should divide each function by its norm. So this line that we had before, of trigonometric functions, now it's normalized, it's normalized by this number. So 1 divided by square root of 2 pi. Then cosinus, we write in this way, cosinus mx divided by pi, sinus mx divided by square root of pi. And from 1 to infinity. Oh. So we get this orthonormal system. We get such orthonormal system in our space L2 from minus pi to pi. We get orthonormal system in this space from minus pi to pi. Now, we can use this as basis. We can use this as basis. So now we can write any f element of L2 minus pi is the sum, there are some coefficients an, or we can write a0 plus sum n from 1 to infinity, an cosinus nx plus bn sinus nx. So we can expand our function with respect to this basis, So this is usual trigonometric series or usual Fourier series. So this is trigonometric Fourier series. Now, no, typically they don't write these normalization factors. So typically they just write f, no, they in books and everywhere. They don't want to, because these normalization factors can be included in these Fourier coefficients, So now we can calculate how, and on this we finish, how this an can be expressed through integrals, not how it can be expressed through integrals. So, for example, how to find an, We multiply both sides. By cosinus nx, and we get f cosinus nx is equal, and here everything disappear. It would be an, and it would be cosinus nx, scalar product cosinus nx. And we know that this is equal to pi an. So the same formula we get for sinus f sinus nx is equal bn. I can directly write sinus nx square of the norm. So this is pi bn. And now if I just multiply by 1, then I get f multiplied by 1. And here would be a0, and here is the norm of 1 square. It is 2 pi a0. And we finish this lecture with formulas for these coefficients an. They are also called Fourier coefficients. In general, we call Fourier coefficients those with respect to orthonormal basis, but by itself cosinus is not, it's just orthogonal, not orthonormal. But okay, so this is 1 over pi, and this scalar product is just integral fx cosinus nx dx. Bn is again 1 over pi integral fx sinus nx dx. And this a0 is a bit, this a0 is different. So A0 is equal integral 1 over 2 pi, integral from minus pi to pi, and multiply by 1 is just fx dx. So we get such formulas. Yeah. And typically course on Fourier analysis is just started with these formulas. They told, take function f and define these numbers and write this series. And then let us study the properties of this series. And then they study these properties of this series without this L2 space, without, because now it is series, or we should finish. This is just series of functions, and we can study its convergence in any point and so on. But if you work in applications, it's always convergence in L2, because L2 convergence is convergence with respect to energy. So we have signal, and we see how the energy of total signal is expanded, is approximated by these guys. It's approximated by its energy in some, each N is channel. For example, in wireless communication, we have channels numerated by N, and then we distribute energy through these channels. Yeah, so this is really this thing. Okay, so it's enough for today, and we continue now to more concrete calculations. We shall calculate for different f, the Fourier series, study their properties. Yeah, and this would be problems for the second part for exam. So if you have some f, then calculate its Fourier series and study its properties. Yeah. Top.